In this video, we're going to talk about carbohydrates with an emphasis on structure. Now, carbohydrates are these energy-rich molecules that you all know about, which are made by photosynthesis, where carbon dioxide and water come together to form these complex molecules. They're interesting because they have the formula which just goes with their name. They're made of carbon and water, essentially. So if there are 4 carbon atoms, there's 4 water molecules. Very simple. And very easy to think about. Of course, these molecules are made by plants, but we use them for our own energy source. So you can take a sugar, you can metabolize it, you get energy, and of course, respiration gives you CO2 and water. Now, the name carbohydrate is one name. They're also called saccharides, which comes from the Greek word from sugar. Saccharide, it's the same as Zachary, Zeke. Greek for Zahari, that's pretty great. But Zachary, you all know Dr. Katsoumanis. Zachary, he's just a really sweet guy. So anyway, we have carbohydrates. So let's look at the various types. So the saccharides come in lots of different forms. Monosaccharide means one molecule, one ring. Here's glucose. You can hook 2 of them together, form a disaccharide. This is maltose, which is 2 glucose, or 2 disaccharides brought together, not 2 glucoses, but 2 disaccharides brought together. We have polymers, starch and cellulose, where you have this 1,4 polymer formed from the monosaccharides. Sucrose, which is table sugar, is made up of 2 monosaccharides, glucose and fructose, so 1 6-carbon sugar and 1 5-carbon sugar. And so there's lots of possibilities, and all kinds of things are known to exist. Now, the types of monosaccharides, the first thing is the number of carbons. The smallest ones that you can have is 3 carbons, and the largest ones that we commonly see is 6 carbons. So it's 3 to 6 carbons. And there are 2 forms. They all have 1 carbonyl in them. So one of the carbons will be a carbonyl. Most commonly, we worry about the aldehyde derivatives. Here's glyceraldehyde, the simplest, what we call aldose. But you can also have ketose, and this is this is a ketotetrose, which is 4-carbon sugar with a ketone. So you can either have aldoses or ketose, and it's a hard word to say. And both exist, and again, from 3 carbons to 6. You get lots and lots of isomers. So both of these, of course, are based upon this hemiacetal structure. So hemiacetals, of course, is something you learned about back some more than a semester ago. Is essentially you have this equilibrium between the open and the closed form. Now, here's an aldopentose, and again, of course, here's your hemiacetal. It comes apart to the open form, and then here's just a molecule drawn in its open form. You can do the same thing with a ketohexose here. This is a 6-carbon sugar. There's an internal carbonyl here, which forms a ketone. And again, these things are available in both an open and closed form. Here is the most famous of all the sugars, which is glucose. Glucose, of course, is a 6-carbon sugar. There's 1 oxygen in the ring, and that oxygen, of course, is part of the hemiacetal. So this is the closed form of glucose, and it has given a special name of pyranose. And then this is the acyclic form of glucose. And again, these 2 are in equilibrium. But of course, when you put this back together, and when you form that hemiacetal, the oxygen can either be pointing up or it can be pointing down. And these are actually different molecules. Once you actually form that hemiacetal, it's all in equilibrium, but these indeed are different molecules. And so what's the relationship? Are they identical? Well, I just told you they're different molecules, so they're not identical. Are they enantiomers? Well, they differ in chirality. That carbon, does that make them an enantiomer? No, an enantiomer, you have to reverse the chirality at all the carbons. Are they diastereomers? Yeah, they're diastereomers. A diastereomer is a stereoisomer, which is not an enantiomer. So these are not enantiomers, so they have to be diastereomers, because they're definitely stereoisomers. They're not diastereomers. That's D is about as false as you can get. So anyway, these are diastereomers, Since they differ at only one particular carbon, we call them epimers, and that's the general definition of an epimer. Is it when you have diastereomers with multiple chiral centers? If you reverse one of those chiral centers, you form an epimer. Now, in this particular case, this carbon is where the hemiacetal is located. It's called the anomeric carbon. It's a special name for the hemiacetal carbon, and that makes these epimers even more special. They are called anomers, and an anomer is simply an epimer where the stereochemical difference is due to a presence of a different configuration of a hemiacetal. And so that's a lot of nomenclature, but it does make a little bit of sense. And because these epimers are special because they can readily interconvert via the open form. Now, if you look at this equilibrium a little bit more, we can see how does that occur. Of course, is the hemiacetal here is shown in the absence of acid-base catalysis. It's just you would kick out an O minus to temporarily form this oxonium ion, which of course then could rotate around the carbon-carbon single bond to simply go to the other form when it closes up the second time. So this is what was called mutarotation, where you're essentially changing isomerizing the stereochemistry of the anomeric carbon, and this is something that goes on all the time. Now, in simple glucose, of course, these two ring forms are not equally populated because, well, this one down here has an axial OH, this one has an equatorial OH, and the equatorial is a bit more stable. So 64% of the glucose is what we call beta glucose, and only 36% is alpha. And the open form is sitting there at 0.003%. Not very much, but enough to do the interconversion. And so there's always a little bit of the open form present, and the two closed forms, the two different forms of pyranose, are always in equilibrium. Now, the interesting thing about this is that the open form, there's enough of it around for the compound to do reactions as an aldehyde. So you can do reactions of aldehyde with a sugar, even though only this 3.003% is formed at any time. Now, there's a lot of nomenclature we have to worry about. With a ring drawn in standard orientation, by that we mean the oxidant at this particular position. You're just going to always going to draw these rings the same way. So we always put the oxidant at that position. And if there's this one hydroxyl group, there's one carbon which is not part of the ring, the CH2OH. If that is on what we call up, okay, then this is designated as a D sugar. And most of the sugars we deal with are D sugars. So when you see these things drawn in this standard orientation, normally this group will be up because it will be a D sugar. Now, there are L sugars. We have to worry about the L sugars, but the D sugars are the most common. The other piece of nomenclature we have to worry about is whether the anomeric carbon OH is up or down. And the rule is here is if it's trans to the side group over here, okay, which it means in this case it's an axial OH, we call that alpha. If it's cis to the group over here, we call it beta. So trans is alpha, cis is beta. Now, if the side group is equatorial, like it normally is, because it's the biggest group, then it means that the trans one will be axial, and the beta one will be equatorial, and generally beta is more stable. But that depends on the configuration that you've drawn it. So let's look at a question on this. So here are now 5 sugars, different sugars. Some are 5-membered rings, etc. 6, which is a beta L sugar. Now, I said the standard orientation is you want the side group here to be up for a D. So for an L, we're looking for it to be down. So which ones have this group down? This has the group down. Well, here it's up, there it's down, here it's down, here it's up, there it's down. Okay, and beta, okay, the OH has to be cis to that side group. So let's look. Here it's down, there it's up. Here it's down, The OH is down. So this is cis. This is good. And then the other one was over here. This one's down. That one's up. This is trans. So which one had its cis? C had a cis. So C is the beta L sugar. And that's a lot of nomenclature, but you just have to get used to it if you're going to look at all these compounds. They really do all look alike. Now, one of the problems is drawing these things in different orientations. So here is the glucose in its two isomeric pyranose forms and the open form over here. Now, the open form, I've drawn it here. We've broken up the ring, but these are more conventional drawings of the open form. How do you read these things? Well, what you have to do is imagine having a model here, this and just kind of opening this guy up so you preserve the zigzag. Now, if you think about this a little bit here. So here's the aldehyde. We got it on the end here. So that carbon, there's no orientation we have to worry about for the aldehyde. This could be up or down. It's not going to change anything. But this carbon would be up, okay, and that OH would be pointing out toward you, all right? And then you would push this next carbon down, and again, the OH would be pointing toward you, so it would be a wedge out. This one would be, then this last one would be up, okay, and it's pointing again toward you. So we're going to have three OH groups, and in the particular case of glucose, the first three are all going to be OH pointing out toward you. Now the last one is a little bit harder to see, but you're going to have to, now what you're going to have to do is twist such that the chain continues along the side group over here. So when you twist this around, this OH here will actually be back. So the answer here is D. Okay, and if you look upon all these drawings except B, I have this OH group back, and this makes them D sugars, it turns out. So the position of that group here, this OH group will always be back in these drawings if it's a D sugar. This is, as I say, the best way to do this is to get yourself a set of models and try to figure this out, because it's really hard to do it on a piece of paper. So I would hear a case where break out those models which you haven't been using all term. This is a kind of a complicated thing to draw. Now this is another way of drawing it. This is called a Fischer projection. In Fischer projections, things really get weird. In a Fischer projection, what you do is you take all your carbons and you put them basically in a U-shaped thing where you take all the carbons, you make all the carbon-carbon chains eclipsed, and then you take that model and you turn it away from you. So in looking at this drawing down here, which is called the Fischer projection, the aldehyde is back, the CH2OH on the end is back, and all the carbon-carbons are eclipsed. And so that's a very weird configuration of a molecule. And the way you do it up here is you basically just take this ring and you force everything to be planar, arbitrarily. And you force it all to be planar, and then the bottom side of this molecule becomes the right side over here. So if you think about this, you're going to force everything to be planar. Okay, so if you force this to be planar, this OH will be down, this one will be up, that one will be down. And so if you come over here, this is right side, left side, right side. Right side, left side, right side. So down is to the right. And then again, the anomeric, the penultimate carbon down here. We have the CH2OH group down here. This is penultimate, means next to the ultimate. That's this carbon. In D sugars, this will always be to the right. So there's no ambiguity down here. If it's D, this OH is to the right. The exact identity of the sugar, otherwise though, depends upon the positions to do these OH groups, and they could be either on the left or the right. So this is a Fischer projection, and this is the way that most people will draw these things in a systematic way. The other way of drawing them is to get away from the chair and draw these things which are called Hallworth projections, which basically just flatten out the ring, and you can see the relationship here. And again now, the relationship between the Hallworth projections and the Fischer projections are easy to see, is you just go around and the bottom carbons here are the right-hand side over here. And so the kind of way to think about this in your mind is start with the conventional chair, go to the Hallworth, and then to the Fischer, and you should get everything correct. So now how do you go backwards? Well, again, going backwards, what you imagine is that these lines are all the carbon card change is bent back away from you, and so that's just the conformation of the molecule. You think of a model, you simply take all your carbons, make all the carbons, so all the carbon-carbon bonds are eclipsed. That means no matter whatever the length is, it'll be kind of a U-shaped structure, and then you just read off the stereochemistry from that. And so here, in this case here, if you look for your eyeball from the top, okay, and you put the aldehyde on the top, this OH group has to be on the right-hand side because it's a wedge out. And it's just the way it works. You can number these things, and that'll help a little bit. The last carbon, in this case it's the only OH, determines whether it's D or L, and if it's on the right, it's D in this case. That's pretty sensitive. So this is D-glyceraldehyde. In this case, there's only one stereochemical center, so it's an enantiomer is L-glyceraldehyde because you're flipping just the only OH in the whole molecule. Let's do another one. This is L-threose, and what we want to do is determine which of these molecules is L-threose. Now the way you want to do this is you got to imagine in your mind that, again, the 4 carbons are not in the configuration down here. You got to do a rotation to bring all the carbons they're all eclipsed. So this would be up here, but then you got to rotate around this bond to bring this OH down. So you want the 4 carbons, like this, and then the right-hand side is going to be the front. The right-hand side is going to be the front. And essentially, what you're doing is you simply have to do a rotation around this center bond. So can you stop and figure out which one of these 4 molecules is L-threose? This again, it hurts your head. I'm not saying this is easy. So stop the video, see if you can figure this out. So how would you do this? Well, this is another drawing to kind of help you. So again, we've rotated around here. So this molecule, which one of the 4 is this? So you got to rotate around that single molecule right there. Now the way to think about it, if you right now these two OHs are on the same side, but if we rotate, think about keeping the bottom of the molecule stable, and we're going to rotate this side, so that'll flip the sides of the OH and the H up here. So and the right side is the front side. So if we're going to rotate here, it'll put both OHs on the back. Which of these have both OHs on the back? D has both OHs on the back. So it's going to be D. Now, another way to do it is you can name the stereochemistry. Get out your thumbs and figure out which is R and which is S. That's R, that's S. You go through and name all the bottom ones. That's SS, there's RS, there's RR, and here's our RS starting from aldehyde in RS. So it is indeed D. That's complicated, but this is something you really need to be able to do. And it's enough to, like I say, hurt one's head. So you got to practice a little bit. Now, how can you go from the Fischer structure to the cyclic structures? Well, the way you do this is again, I'm simply drawing out the aldehyde here. You're going to form a ring, but the good thing to do first is to number the carbons. So we number our carbons, okay? Then draw a ring structure containing the carbons 1 from the aldehyde, okay, until the penultimate carbon, which is penultimate means next to ultimate, so to this carbon right here. So our hemiacetal is going to be between this OH and the aldehyde up there. So that's going to be our ring. And now determine what's D or L. Okay, if it's on the right, it's D. So this is a D sugar. And in the D sugar, the last carbon will always be up. So I'm going to draw this thing in the standard orientation. And the anomeric carbon can be either up or down, whether it's alpha or beta, cis or trans, to the CH2OH. So now you place the remaining groups on the ring in the following fashion. Right side is down, left side is up. supposing we're in the standard orientation. So here we go. So the standard orientation means the anomeric carbon there and the oxygen next to it, and then here's the CH2OH. So we put it up, okay, because it's a D sugar, okay, so D sugar, the last carbon is up, so we draw this one up, okay, and then we haven't said whether it's alpha or beta, so that's why the squiggly line here means that this OH could be either up or down depending which one it is. And then the other OHs, okay, so this is carbon 2, all right, so right is down, left is up. So here it's left, so the OH is up. This one is right, so the OH is down. So this is how you draw this particular one. This is indeed complicated. I can't disagree. So let's see if you can do this one. So pause this video, see if you can figure out D mannose. Now D is indeed the standard sugar, so you want that side group to be in the standard orientation, and it is here in, well, all of them except E is an L sugar, so E is you can throw out because the CH2OH is down here. A, B, C, and D all have it up. So you have to figure it out. Now we're looking for alpha, okay? Now in the case of alpha, it means that the anomeric OH is going to be trans to that side group. Or in the case of a 6-carbon sugar, that in the standard orientation, this means it's going to be axial. So have you got it figured out? Have you got it figured out? So again, right-hand side, this is the downside. So we're going to be OH is up, up, down. Okay, up, up, down. Which one has it up, up, down? Okay, can you find it? So, okay, so let's go through this. D sugar, it's A, B, C, or D. It's alpha, so the OH has to be trans to the side group. So A here is alpha, D here is alpha, B is beta, and C is beta. So it's either A or D, and then the OH groups, the right-hand side is down, the left-hand side it's up. So here we have up, up, down. So up, up, down. It's D. So this is D mannose, is D. That's a lot of work, but as you can say, these are really different molecules, and in nature it makes all the difference in the world. We need to be able to tell these apart. So so how many stereoisomers are actually dealing with? Well, we have here. We have all these different chiral centers. We have 1, 2, 3, 4, actually 5, but this one here is the anomeric carbon, and those rapidly interconvert. And because they rapidly interconvert, that's the alpha or beta, they're really the same, they're different structures, but they're not really separate molecules because they're in direct equilibrium with one another. So we don't consider alpha and beta glucose to be different molecules. So we have 4 chiral centers that we have to worry about. 1, 2, 3, 4. Now the one back here where the side group is, those are, that makes the difference between a D sugar and an L sugar. The D sugars are the most common ones, and so of these 16 different possibilities, 8 of them will be D, 8 of them will be L, and so the 8 depend upon the relative stereochemistry of these 3 positions, because of course 2 to the third, you get 2, 4, 8, so there's 8 different possibilities. And here they are, okay. Here's glucose in the middle here, but there are 8 different possibilities, and these are all D sugars because this penultimate carbon, the OH, is on the right. If you're going to make a diagram for the L sugars, what you would do is you just flip everything from the left to the right, and you got to remember, flip them all. So L-glucose has everything switched, okay? Not just the penultimate one, but everything switched, because it's the true enantiomer. Now you can, as you look for the shorter sugars, the 5-carbon sugars, there's 4 of them. The 4-carbon sugars, there's 2 of them, and then the 3-carbon sugar, there's just 1 D and 1. Well, there's 4 D 5-carbon ones. There's 2 D 4-carbon ones. There's 1 D 3-carbon sugar. And of course, this you could reproduce this whole diagram for the L's. So that's our look at the sugars as a whole. And one of the last thing that we need to talk about is the relationship between one of these things. So what if you took the C5 epimer of D-galactose? So where is the galactose? Over here. Now the C5 epimer, what it means is flip the stereochemistry just at that carbon. So what would you name the epimer, the C5 epimer of D-galactose? So what you need to do is change the stereochemistry at this penultimate carbon from the right OH to the left OH. Okay, so now name it. All right. Well, it's no longer a D sugar. This became an L sugar. But which L sugar is it? How are we going to figure this out? Again, can you stop the video and figure it out? Okay. Well, let's just look at this. So here is our D-galactose. What we're going to do is we're going to summarize at that carbon. So this is the C5 epimer. We've changed the stereochemistry here. And so what is this molecule? Well, this molecule, of course, is not in the list up there. Why? Because it's an L sugar. But what's its mirror image? What's mirror image is this guy. Is this one in the list up here? Well, let's go look. Ah, it is. It's right there. Right there. Look at this. So this is this. There's we go left and then 3 rights. Okay. So this right here is D-L-threose. So which one's this? Well, if this is D-L-threose, this has to be L-L-threose. So the answer is L-L-threose. And so that's how you figure these guys out. Not that bad, but it's still, you just have to, think about it slowly and go through these things one at a time. Okay, so how can you interconvert these things? You just use your enolate chemistry, which you already know about. So this is a here we have our simple 3-carbon sugar. And how could we summarize this? Well, if you had some base, you could simply form an enolate, okay, and form an achiral enolate, and then the OH could come back, you could reprotonate that using a water, and you could easily go back the other way. So all this stuff is in equilibrium. This is of course, all happening at the same time, and as you simply recover here, you have racemized that carbon. So we're starting off here with actually not. I'm sorry. This is not a sugar. This is the ether of a sugar. I'm not paying attention to what I'm talking about. But you're simply, you can go via either the enolate, or you can go via the enol. I'm not sure why this part here isn't actually even necessary. I mean, this is just going from back, just showing you this is all in equilibrium. But I mean, the base simplest mechanism, you just pull off the proton, and then you put it back on the other side, and you can racemize these things. And this is happening all the time in all these sugars, of course, but very slowly, thank goodness, because it generally requires acid. If it occurred at a very fast rate, you need acid or base catalysis, and you normally in nature you don't have that. You're not in strong acid, you're not in strong base, so these things are not happening so fast. Now here I have D-ribose. Okay, so this is a 5-carbon sugar. And you can form your enolate, and you can just form the epimer here, which in this particular case is ribinose. So all you've done is convert from one sugar to another by flipping that particular hydroxyl group. But on the other hand, you could do this. You could do an isomerization to convert from an aldehyde to a ketone, because when you get at this particular stage here, since you have an OH here and an O- there, you can just flip that proton over here, and that's called a tautomerization. And so this also shows is that the aldehydes are in equilibrium with the ketones, and so sugars can convert back and forth between aldoses and ketoses, again, just by inlay chemistry. Or you can do this whole thing actually using acid catalysis as well, except we normally think in cellular system the pH is a little bit above 7. So thinking is using an OH as your catalyst is a little bit more realistic. So that's an introduction to the structure of sugars. It's very complicated. I won't say this is the world's best lecture, but you just have to work through these problems one at a time and try to figure out this stuff. So good luck.